Hi. Last time we introduced the idea of a feedback system, and we spent some time looking at what's really the fundamental property of a feedback system, namely its ability to desensitize the closed-loop transfer function to changes in the forward path gain. And we found out that that sort of desensitivity is obtained really only in exchange for starting with a larger amount of forward path gain than we actually need. We then looked at the way feedback can modify impedance levels in a feedback system. We illustrated this with an electronic system, an operational amplifier, but the same kind of modification goes on in mechanical systems. If we ask for the output stiffness of a servo mechanism, we get the same kinds of relationships. That's a mechanical impedance rather than an electrical one, but the same general kinds of things happen. Today I'd like to continue looking at basic properties of feedback systems. I'd like to look at how feedback systems modify noise injected at various points in the loop, and also see how feedback can be used to moderate certain kinds of nonlinearities. Let's consider the system that we show here. And here we have a system with an input, output of course, a feedback transfer function or a feedback element that monitors the output and applies it back to the summing point. And then what we've shown, in addition to our input, presumably the output is supposed to be some function of the input, we have three disturbances that are injected at various points in the system. Here we have a disturbance that's injected at the same point that the actual input signal is applied. We have a second disturbance that's injected after some gain in the forward path, after the gain A1. And we finally have a third disturbance that's injected after another amount of gain has been achieved in the forward path. If we were looking at a physical system that this might represent, why, we could consider, for example, some sort of an audio amplifier. We have an input signal and a disturbance injected at the same point as the input signal. Might be noise associated with the pickup. For example, if we have a audio reproduction system, noise injected simultaneously with the input signal or at the same point in the system would be noise that was picked up by the cartridge that was tracking a record, for example. Our second noise source might be noise that comes in, for example, at the output of a preamplifying stage. We have an amplifier, maybe a transistor amplifier, that's providing the package of gain A1. If there's some noise on the supply voltage associated with that amplifier, the output stage of the amplifier is oftentimes dependent on the supply voltage as well as on its input signal. And so our second disturbance might reflect noise introduced because of an improperly regulated supply associated with the preamplifier, or a noisy supply associated with a preamplifier. And then finally, we might consider the third disturbance, which occurs near the output of the system, as reflecting noise associated with the power handling stage of our final amplifier. And so if we were thinking about an audio system, this might be the physical significance of the various disturbances that are shown. Well, here we have a system that actually has four inputs, a desired input, and then the three noises that we talked about. And we can, of course, write the output as the superposition of the responses to those four inputs. When we do that, we get VI times the forward path over 1 minus the loop transmission. That's always the expression that we get for a closed loop gain, and we saw that last time. So we get VI times A1, A2. That's the forward path for the VI input. The loop transmission for this particular system, again, we can break the loop. We get a minus A1, A2, F for the loop transmission. Consequently, 1 minus the loop transmission is 1 plus A1, A2, F. So the relationship between the output voltage and the input voltage is the forward path, A1, A2, over 1 plus A1, A2, F. Since the first disturbance is injected at that same point, the transfer function relating the output to the first disturbance is the same as that which links the input to the first disturbance. Similarly, when we calculate the output in response to the second disturbance, we get its forward path, which is A2, over 1 minus the loop transmission. The loop transmission is the same for all cases, so we get A2 over 1 plus A1, A2F. Finally, when we look at the third disturbance, we get its forward path simply 1 over 1 minus the loop transmission. We get 1 over 1 plus A1, A2F. I've repeated those expressions here, and simply repeating that the output voltage is A1, A2 over 1 plus A1, A2F times VI plus A1, A2 over 1 plus A1, A2F times VD1. The gain from the input and the first disturbance are exactly the same since they appear at the same point or are applied to the system at the same point. Plus A2 over 1 plus A1, A2F times VD2 plus 1 over 1 plus A1, A2F times the third disturbance. I think we can get a little better emphasis of the important features, the important feature of this expression by factoring out the A1, A2 over 1 plus A1, A2F. When we do that, we get that factor out in front. Then we get VI plus VD1. We get a VD2 divided by this. This should actually be A1. I'm sorry. This should be A1, and this should be A1, A2. So we get a VI plus VD1 plus VD2, the second disturbance, divided by A1. The important point there is that the quantity A1 is the gain in the block diagram that precedes the point at which we inject noise. If we think back to our original block diagram, we had the disturbance injected after an amount of gain had been applied to the signal channel, and the amount of gain was A1. Similarly, when we inject the third disturbance, the gain that precedes it, the gain that appears between the input signal and the third disturbance, is the amount A1, A2. And so when we factor this term, we get an A1, A2 dividing the relative magnitude of the third disturbance.